Mechanical Engineering at Adi Parasiti Engineering College, and my guide is Dr.R.Senthil, who is a professor in my own college. And today's topic is motion planning for Concertina and lateral undulation motion mechanism in a snake robot. And an overview of it. First, I'll talk about the introduction and the modeling parameters which I took for the making for this motion planning. And next is the motion planning parameters. And then the position of the robot in the 2D plane, and the angles of rotation, the Concertina motion, and so on till the dynamic analysis in MSc Adams, and comparing these two with the other motion planning techniques which are already available. And coming to the introduction, a snake robot plays an important role in exploring surfaces which are really rough in nature. And in this paper, we are discussing about the motion planning for the two motions, that is Concertina and lateral undulation. And this motion planning will actually help in dynamic analysis simulation, which I've already done, but we haven't mentioned the paper, but I'll be telling it about that. And next is the coding, that is the motors which will be coded, using a microcontroller. The next thing which I like to tell, this is a continuation of a previous work, that is a conceptual design of lateral undulation and side winding motion mechanism, which was presented last year in a conference conducted by IDES at Bangalore. And these are the modeling parameters, a model of the snake robot which we have designed. And this is the segment 1, segment 2 and the segment 3, and this are the connectors between the two segments. This segment 2 has a propelling unit which propels the segment 1, and segment 3 has a propelling unit which propels segment 2, and segment 3 moves by due to the action of segment 2, because the segment 2 will be pulling the segment 3 in front. And these are the brake pads which are present, so that it stabilizes itself on the surface and pushes the other segment forward. The next thing is the motion planning parameters. This is the top view of the robot. The yellow color things which are blocks which are represented as the motors. Motor 1 and motor 2 will be propelling these two links. Motor 3 is a link which is used to control the brakes, and the motor for the first segment there's no propelling unit. And now we'll be positioning the snake robot in a 2D plane, because this is the usual first step which is done in motion planning, and this is a reference which I've taken from other papers. And this is our snake robot which is positioned in the XY plane, and we are considering a 2D plane for the motion. And this is the angle of rotation of the turning rods which are present, and we'll be representing it as 0 to 180 for half rotation, or 0 to 90 to 270 for half rotation. These are two angles which we'll be representing. And this is the Concertina motion. Concertina motion is nothing but a snake will be just compressing itself and moving forward. Due to compression and expansion, the snake will be moving forward. This is the 2D sketch of the snake robot, and this is the 3D modeling of the snake robot which are made. And these two motors will be pushing it forward. This is the basic mechanism. When this is pushing forward, the motor 3 will be activated so that the brakes are pressed on the ground, so that it stabilizes itself. And next thing is a motion planning sequence. This is actually a table which shows the angle of rotation of the connecting rod present in the brake, present for braking. Braking is nothing but this section of it. This motor angles up. Angle of the connecting rod is shown here. And next is the Concertina motion, that is the motion of these two, motor 1 and motor 2, and are present here, M1 and M2. And there are 4 sequences which will be repeated so that the motion is executed. And the first action sequence is the motion segment 1 and 3 move forward. The second action sequence, the position of the brakes are changed so that the stabilization of this changes. And the third thing, the segment 2 moves forward, and again the position of the brakes are changed, so that it can actually come from the step 1 and continue, so it can keep moving forward. And this is the sequence of action, and the red thing represents that the brakes are off, that is, it's lifted off the ground, and the green thing represents that the brakes are on, as we have shown here. This is on, and the third segment is off, and this is the off position of the brake. And the orange color thing represents the transition of the 3 brakes, so that the brakes changes itself and it becomes green, that is, it's on. And again the transition occurs, and these 4 steps are repeated so that the motion is continuous. And next thing is a lateral undulation motion, for which a motion planning is also done. Lateral undulation motion is nothing but a bending of the snake as it moves on its path. This will be very useful when the snake robot is going to explore a new area, so that it gets a full image of the area which is in the front. And this is the tabular column for the motion planning sequence for the lateral undulation motion. And here there are totally 8 sequences which are repeated, as I told earlier. These are repeated, and if you're going to look at this, first 8 will be like this, and for the turning towards the other side, the sections from 9 to 16 are there, so the snake moves in a bending nature. And for this, these values which are actually, which we are denoting, this is used for dynamic analysis, for which we are using MSc Adam software, where the syntax for the coding, the function in MSc software is that step is a step function, and the parameter which is used is a time, and the start time, that is a time which the motion starts, and the start position is the angle which we already mentioned, that is 0 to 180 or something, and the end time is the time till which the action is performed, and the end position is the end position at the end of the robot, the end of the completion. And this is an example. In example 1, like step function is used, at the 0 second the position will be 0, and the 8 second it will be 0. That is, during this time the link is idle, it is not moving. And from the step, second thing, time 8, that is from the 8th second till the 10th second, initially it is 0 and it moves to 180, and it goes on like that till the end of the motion. And this is the dynamic analysis screen, where we'll be writing the angles, representing the angles in the function builder, and this will be implemented, and it can be stimulated actually. And this is comparing our motion planning technique with other techniques. Usually they use a rotational matrix using cos and sine, so to represent the robot in a 3D plane. And it is simple as when only one link is used. But if many links, like if you're going to see here, here's a link, here's a link, here's a link, totally 23 links are there. And for such a complicated mechanism, we cannot be using the rotation matrix and calculating for each and everything. So we have developed this sequence, the tabular column. These sequences can be easily used, and they can be analyzed. The motion planning can be done. And coming to the conclusion, thus we have created a motion planning sequence for the snake robots, which we have already, mechanisms which we have already presented, and the modeling was done. And then this motion planning can be used for dynamic analysis, coding, and this makes coding more easier. And these are some of the references. Thank you.
Show the snake. So this yellow box is motor.
Yeah.
So it's moving in which direction?
It's going to move in the forward direction.
So don't you think that placing the motors on the second part of it, second part will push that first part?
Okay.
So our requirement will be, why don't you put these motors on the first part of that robot?
And pull it forward.
Just to pull it forward. So it's just like placing engine on the bogie first and then engine. What do you think of that?
Okay, I will try it out while stimulating it.
It's a very basic thing which like motors which will move the snake should be on the first part of the
it can be okay for that, but on the last segment is this program. You cannot place it in there. First segment is okay. You can put it. For the last segment, we have to again place it at the back. Maybe you can change it for the first segment, but for the last segment you can't do it.
You can put this on all 3 parts of it.
Power segment will be more. So 2 more motors are going to have to be added.
Then don't put on second part, put on first and third part.
For the similar thing I done. For the first thing it's not there.
No, that is for brakes, no?
That is for brakes.
First part. This is for brakes.
Yeah.
Okay. For pushing it forward, that force will be generated by second part.
Okay.
Second part will push first part. Is it so?
Yes.
So don't you think that these models should be put on first part?
I mean, it don't make a big difference because we are having a caster in the beginning. As we have shown, casters will be down, the four ball bearing, something like that will be there, and it doesn't show much difference because friction is limited using it. And if your brakes are applied, means this caster won't move.
You not show me an algorithm?
Algorithm, I haven't shown, but
I think you included in the paper.
yeah, included.
So you have implemented this algorithm?
Yeah, I've implemented it, and this is the screenshot of the stimulation.
You have implemented this algorithm in the simulation.
Stimulation.
Did you notice the performance?
Yeah, I've noticed the performance, and I'm trying to calculate the torques which are required in the motor, and based on the torques and power required, I'll be buying a motor for my final project.
You don't see any comparison with the existing?
I compared it about the motion planning technique.
It's only the comparison in terms of how better your system is performing and all that.
I haven't done
Another thing is, when it's in the planning stage, of course, it's very good to see that it's logical, but when it comes to the implementation level, when we design a mechanical and electronics part of this particular robot, I don't know how better your system will perform.
dynamic analysis is okay. We have simulated the dynamic analysis. We have also taken the video. And it is performing well, the dynamic analysis.
No, that's simulator.
Yeah, the simulator. We have studied the curves for each and every link, and it's quite satisfactory.
When it comes to the implementation level,
It's almost the same because Boeing company uses MSc Adams for simulating the landing gears of the aeroplane, and it is almost closely accurate, this simulator, and it's satisfactory. That's why we are using MSc Adams for it.